probably switch on the mic. Is that good? Yeah? All right. Yeah, so as you said, my name is Jarrett. I work with the Julia group at MIT. I do a couple of different things in different areas, but probably my favorite area to work in is probably automatic differentiation. And so before I kind of get into the weeds, just a show of hands, how many people have used code to take derivatives here? Okay, so we got some hands. We got a waving hand in the back, very exciting. How many of you have written code to differentiate other code? Oh, only one waving hand, but still waving. Good. Okay, so that gives me, I guess, a feel for the background here, and that's good. So we're going to start off just talking about generic numerical derivatives and what you might do if you ran into this problem. So you have a scalar function, and maybe your colleague implemented it, or you implemented it, but don't want to read the code because it was horrible and it was a long time ago. But anyway, it's like a black box function, and you just want to take the derivative of what do you do. So this is kind of the problem space that I'm working in when I'm trying to write libraries that can differentiate code for users. So kind of the first thing that people would try normally is what's called the finite difference method. So in this method, you're essentially using the standard limit definition of a derivative and just approximating it by adding a really small perturbation to your input and then just seeing how your function varies along that input. So this is an extremely common method because it works really well out of the box. If your code runs and produces sensible output, you can probably use this method to take derivatives. It is not so great when it comes to performance or approximation error. So there is a truncation error, which you can eliminate essentially by making h here really, really small. H is referred to as the step size. So you can make h really, really small, and that truncation error, the term at the end there, will drop off, and that's nice. But if you make h too small, h will tend to 0, and then you'll just be doing f of x minus f of x, which is not a great derivative. I mean, it's just 0. So there's subtractive cancellation error as well that you have to worry about, and it requires 2 evaluations of your input function. You know, you'd hope you'd be able to do a little bit better than that. So people thought about it, and they were like, well, you know, I don't really like this method a lot. So they came up with this, which is the complex step method. And so basically, what you're doing here is you're taking your step size and using it as a component, as an imaginary component of a complex number. And then if you compute a Taylor series with this guy, you can basically prove that most of the higher order terms kind of drop out with some error. And then you can essentially get a derivative out by looking at the imaginary component here. And so this is a pretty cool method because you're only doing one call to f. There's no subtractive cancellation error, so you make h really, really small, like machine epsilon small, and then your error will be on the order of machine epsilon. A lot of languages support complex numbers pretty well, right, too, so that's good. So it's nice, but it has some problems. I mean, so complex number operations are often slower than real number operations. Maybe okay for you, depending on your use case. But if it is okay for you, depending on your use case, then that means that you're already probably working in a realm where you're doing like complex computations anyway. And if that's the case, you might not want to use this method because it can be unsafe. Essentially, what you're using the imaginary number here to do something kind of hacky, and it can get confused with actual complex calculations if you're trying to differentiate it like a complex function. This also requires either operator overloading or source transformation of the code for it to work properly, which in a lot of languages can be a pain. In Julia, it's fairly nice, but we also already overload a lot of operations on complex numbers, so maybe it's not the best idea for us. So if you were really bored and it was the afternoon and you had lunch and were tired and you're like, I'm just going to scroll around Wikipedia for a while, you might run into this guy. This is the dual number method. So essentially, this is kind of like the complex step method in that you have a scalar with a perturbation with some extra component tacked on. And so it's kind of like a complex number. except instead of I squared equaling -1, we define it as epsilon squared equals 0. But epsilon itself isn't 0. So the way to think about this, I guess, is just kind of like an infinitesimal perturbation along the number line. And so you can kind of prove that if you do a Taylor series expansion of something like this, then the epsilon components for higher order derivatives just cancel out and go away because they all go to 0. And then you get basically an exact derivative right out of it. So there's no approximation error. It still only requires one call to f, which is great. But it can be difficult to implement in some language performantly because your code has to accept generic number types, and a lot of times that can be slow in some languages. And like the complex step method, it requires operator overloading and/or source code transformation. So here's a plot of just like this error comparison. So what we see here is we have high step size over here on the right, and then it gets lower and lower and lower. And so the scaling of the truncation error term for both the complex step method and the finite differencing method is pretty much the same until you get to a certain point, and you get around here. And then you start running into the subtractive cancellation error. So now your step size is so small that you're not really varying your input enough to get anything meaningful out, and it's just going to go to 0. So the error eventually just goes straight back up to the order of the input. And as you can see, you can just keep decreasing the step size for the complex step method, and then it levels out at machine epsilon. And then just for the sake of completeness, I plotted dual number approximation error, which is machine epsilon. It's on the order of whatever the approximation error was in your original function anyways. It's exact derivatives. So there's also performance comparison here. And this function over here is just kind of a toy test function. People like to test these weird scalar derivatives simply because there's a lot of different operations. We've got like exponentiation and trigonometry and squares. So it's kind of has a little bit of everything. And so what we find is that the complex step method, even though it's only one function evaluation instead of 2 for finite differencing, it's a bit slower just because it's actually having to handle the complex component. And this dual number performance comparison was done with with 4diffs dual number. Now 4diff is a package that I wrote and maintained for doing what's called forward mode automatic differentiation, which heavily relies on using these kinds of dual numbers to take derivatives.
Can I assume that the group are essentially 2 calls to f?
Yeah.
Really, it's slightly more expensive than 1 call to f.
Yeah. So it's a bit lower overhead. So, and so that's all well and good. But I mean, how many of you are actually trying to take scalar derivatives all day long? Probably not many. So what we really want to focus on and what people need usually are gradients and Jacobians, so higher dimensional derivatives. And we can actually kind of coerce our dual numbers into doing something nice for us that will give us these things. So we have our nice definition for the gradient. It's just a bunch of partial derivatives, a bunch of directional derivatives. And we have essentially a method that allows us to compute scalar derivatives. It maybe allows us to compute directional derivatives when the function is scalar valued. And so if you just kind of combine these ideas, you can do this by essentially appending the perturbation along each input dimension. And what you get out is the directional derivative along that input dimension. And so that's cool, but if you wanted to get all of the partial derivatives then, you have to go in and seed every single input dimension, and then you need to take in calls of your original function. That's not great, right? We kind of have this dual number, and it's almost like engineered to take derivatives, so why can't we just like engineer it to take take gradients more efficiently? So it turns out you can. So you can extend these dual numbers. Here's our original definition. And so what you can do is instead of saying you have one epsilon component along one real number line is you have n epsilon components. And so if you define their cross products essentially to be 0, then you can think of them as perturbations along different dimensions. And so the number now we're working with is this guy, and that's sometimes called a generalized dual number or a multidimensional dual number. And so how you actually use this guy is you take and append the different perturbations to all the different input dimensions. And then what you get out is essentially along every component, along every epsilon component that you've stored, you have a directional derivative, and so that is essentially the gradient. So when we look at this guy, and we have to think, okay, maybe you could understand how to implement this grayed out guy here, where he's just two scalars, right? And then you have to maybe overload some operations on that type or class or whatever to make that work. But with this new dual number, we have to store a lot more. So we have to store a real component, a scalar, right? And then we also have to store a bunch of these epsilon components. These are the things that allow us to do this seeding here. We just set all the ones that aren't epsilon 1, for example, to 0. And that way it will work out. So naively, one thing you might do is say, we'll just stick them in an array. My class or my struct or my type or whatever will just be a scalar with an array of these epsilon components. And so that is perfectly fine. But in a lot of memory-managed languages, if you just naively start allocating an array for every scalar, these arrays are going to be heap allocated. And so compared to something like a scalar, which can be stack allocated, the heap allocated structure is going to be much slower to essentially talk to and pull data out of and load data back into. So for some of you that have worked on implementing these kinds of things before, you might think, well, if I do this correctly and I make my algorithms like cache friendly, then I shouldn't really even see the difference in terms of loads and stores when actually using them in practice, because the machine will know how to pull things into memory efficiently for me and cache everything correctly. But the problem is, in reality, these arrays are going to be so short-lived and so rapidly allocated that you'd have to find very special cases in which your cache is going to be able to actually optimize this well. So there's also another problem, specifically for Julia, but I wouldn't be surprised if it was a problem for other languages as well. When you heap allocate something in a memory-managed language, your GC has to keep track of it and understand its lifetime. And for a generational garbage collector like Julia's, it means it's going to have to hold on for a while. And so what we've seen is, and this is how I originally implemented these guys, what we've seen is that the overhead for garbage collection was like maybe 80% of the total computation time for a lot of my test functions. And so that's absolutely ridiculous. And so what we decided to do was we can just fix this by stack allocating these components. So how do you do that in Julia? Well, let's talk about it. So what for_diff provides is a wrapper type around a tuple. And so tuples in Julia, kind of like tuples in Python or other languages, are just you have a parentheses and then you have just a list of items, basically. But tuples in Julia are special because they're essentially fixed size stack allocated vectors where the compiler specializes on each of the elements types, each of the type of the elements. So for_diff, the code to actually implement that isn't really that interesting or exciting. It's just wrapping a tuple and then providing a lot of array-like functionality for tuples, like scaling, for example. And so I've omitted it here. But the thing we want to really look at, I guess, is the dual number implementation. So types in Julia can be either defined with this type keyword, or if you don't want the fields to be able to be mutated, you can define it as an immutable. And if you define it as an immutable, then the compiler can take some extra license with the structure you're working with and optimize it in different ways. So these guys are immutable. They're a subtype of real. So I know there's some mathy people in the room. They're probably saying dual numbers aren't a subset of the reals. What? But it actually makes sense programmatically to do this, because we want users to be able to insert these wherever real numbers are going to be found in their code. And Julia's type system is basically nominal in nature, so we can do whatever we want. So So this is our type definition. This is what the structure is. So we want to define some behavior on this. And a very common idiom in Julia to define new behaviors on these types is just to overload a bunch of base functions on them. And so what you see here is that you have all of these elementary functions that I'm essentially overloading such that they have the behavior we expect from our dual numbers as defined in the previous slide. We have, so for sine, we compute sine, and then we also compute cosine, and then on the value, and then multiply it with the components that were already there. And so what this is essentially doing is an application of the chain rule at each step in your program. And it's doing it automatically because I've defined it to do it automatically. And so what's nice about this is if you overload enough of these functions, then basically any numeric function you could come up with as a composite of these functions then works because the chain rule works. And so question is, what does this code actually buy us? So with just this code here, we have now derivatives to arbitrary order by nesting dual numbers. And so if people care about the algebra, you can look up hyperdual numbers. That's essentially what this becomes. You can also do complex differentiation now because you can nest the dual numbers inside of Julia's complex number type. And you can take derivatives over custom number types. And so an example of this, if anybody is familiar with, I guess it's called rigorous or reliable computing, we have some people in our lab, and I met some people in Oxford a week ago who do this interval arithmetic. And so apparently people are using this number type specifically to rigorously bound floating point operations and take derivatives while maintaining a rigorous bound. Anyway, so I'd like to do like a real code example just to show you how this works in practice, I guess. So I have this cumulative product function, which you can find in base Julia. This implementation I have here is probably not what's in base. I just kind of wrote it down naively, but it's cool because it has some control flow, it has loops, it has multiplication, it has assignment. So if you like didn't believe maybe the dual numbers would work in these cases, this is a good case to test. Just a word for people who aren't used to using Julia. Similar, this function here. Everything else is probably self-explanatory, but the similar function here just constructs an array of a like type to the array that you give it in like size. So just to make sure we have the theory in our heads when we're doing this. So we have our definition for the Jacobian. It's once again directional derivatives along each of the input dimensions, but now because it's vector valued function, we have essentially a matrix of derivatives instead of a vector of derivatives, and so there's a difference between that and the gradient. But you kind of just do the same thing. For each of the input dimensions, you only need one perturbation that will vary, and then that will propagate along the rows. Yeah, that'll propagate along the rows of the Jacobian and give you the directional derivatives that you were seeking. So very similar like seeding structure to the thing you would do with a gradient. So it's pretty easy if we just limit ourselves to 3 elements. It's pretty easy to write this out by hand so that we can check later. And so I just have this like fake code in the REPL because I'm not brave enough to live code things. So we're using forward diffs dual number type, and essentially what we have here is we take our input vector, just 1, 2, 3, and then we seed it with these perturbations along every input dimension that we care about, and then we just call the function, and through the magic of calculus, we get the right output. And so forward diff essentially provides an API for doing this for you. And I would like to probably mention here, so this is pretty trivial. This is a three-linked vector. It's not that big. But we are, if you recall, I said we're stack allocating all these components. And if you kind of just extrapolate this out to many, many dimensions, you think about this, the storage complexity here is quadratic in the input dimension. And that's not going to scale very well on the stack. So very much more limited memory space in the heap. and if you try to put too much stuff on the stack, it's going to get bloated, and then everything's going to get very slow. So we can't use this, what's called a vector forward mode, because we're doing it along the entire vector. We can't do this exactly the same way for really high input dimensions. Or even just not so high. Anything that's not trivially small, we actually have to partition the space and seed maybe, for example, if I had 100 length vector and I needed to take derivatives, I maybe would only take 10 derivatives at a time. And that way I would only need to seed 10 partial components at the time. All the rest would have zeros. And then I would execute the function 10 times to get the 10 partial derivatives in chunks and then get all 100 out and then have the gradient. And so ForwardDiff also provides an API for you to tune how you actually do this seeding process and manage it, because for different functions, the way memory flows to the function is going to be different, and different chunk sizes will give you different results, and maybe better or worse results depending on what you're doing. And ForwardDiff can automatically select chunk sizes for you, but this is there if you wanted to tune it yourself. So we should probably talk about performance. I mean, that's kind of why I'm sure a lot of you are here. You're like, oh, Julia, I heard it's fast. So let's see whether it is. So one thing we want to ask ourselves probably is like, how slow is the dual type compared to like just hard coding these kinds of operations? And so to view that, Simon actually mentioned this in the last talk. Julia has these really cool reflective macros for inspecting how code actually gets generated all the way from like what happens after type inference is run to the assembly that gets generated from LLVM. So that's what I've done here. I've used what's called this code native macro that spits out the assembly for the thing you're doing. I've used this macro to kind of to show that the dual number type is like a wrapper is basically zero cost. It's like a zero cost abstraction. Now, there are no epsilon components here, so you're not actually going to take any derivatives. But at least this does maybe what we would expect, and is the same as multiplying two integers normally. So that's great. But of course, we do want to actually test the case where there are derivatives involved, and so we can do that. So I've essentially have this function where I hard-coded the operation that needs to be done, and then called it with Julia's built-in tuple types, and call it just with the dual numbers that should be doing the same thing, but like, I don't know, in some languages they'll box this in, or the operator overloading will incur an extra cost. But as you see here, this assembly is basically the same. And so what this should kind of prove to you is that the operator overloading in Julia is fast and it's expressive, and in a lot of languages you're not going to get this, but because it's such a key abstraction for implementing AD, it really makes Julia a great language for this kind of stuff. So that's good. But real people actually probably don't want to stare at assembly all day and then just check a box. They want to actually make sure that things run at a speed that they can use. So we've been comparing ourselves to AutoGrad recently, which is a reverse mode automatic differentiation library. So we've been talking about the forward mode, where you propagate derivatives via the chain rule in one direction. But you can also do this other technique called reverse mode, where you propagate things the other way. And so it's kind of weird, and I'll explain it later. But for now, all you need to know is that the reverse mode automatic differentiation is algorithmically a more efficient method than forward mode. So forward mode takes on the order is like linear number of function calls in the dimension of the input, whereas reverse mode you can take the gradient in a constant time with possibly a large overhead, but constant time, constant number of function calls. So despite this, we find that ForwardDiff's actually ForwardDiff plus Julia is more performant than AutoGrad up to, I would say, non-trivial input dimensions, much higher than we actually thought it was going to be. And so maybe explaining what these numbers are for a second. So we have times in milliseconds here and here, and then right next to it in parentheses here is a metric that people who do this stuff like to use called the gradient to function overhead ratio. And so what this is saying, for example, is that this gradient took 32 times longer to calculate than just calling the function with that same input. So what's cool here is you can kind of, so Rosenbrock, the function that I'm actually testing against, is just a common test function in optimization. But what's cool is you can see the scaling of the methods algorithmically in the timings here. It's really apparent. So this is a linear function. The gradient takes on the order of linear time for forward mode. And so what you see is the combination of those two. You get a quadratic scaling in the timings and a linear scaling in the overhead. And then for reverse mode, you get a linear scaling in the timings and then a constant scaling in the overhead mostly. And so on the very right, we have the ratio of forward diff versus autograd. And so basically, yeah, so up to about on the order of 10,000, you're better off using Julia in forward mode rather than using Python in autograd. And so I will say that autograd's wrapping NumPy, so I'm not doing some really unfair comparison where I'm like doing a bunch of scalar operations in Python. This is wrapping NumPy, so this is definitely a comparison targeting the audience that I hope Julia is trying to target is NumPy users, scientific Python users. We have another function, Ackley, which basically it's also a test function in optimization, but it gives us about the same results. It's still the case that you're better off using Julia with forward diff up to order of 10,000 variables. I mean, obviously, what you see here is that this overhead has grown quite a bit, right? That's why I say Julia plus forward diff, because at this point, this isn't forward diff making this faster. This is just Julia making it faster, because obviously this is an algorithmically less efficient method, which we can see in the overhead. So just talk a little bit about the ecosystem. So forward diff's a fairly popular project at this point. I started working on it last year during Julia's Summer of Code, and it's been steadily improving since then. Had a lot of help from open source contributors, which is quite great. And so a lot of the people who write these packages have contributed back to forward diff. But it's being used for like a wide variety of applications. And specifically, I work with a guy called Miles Lubin at the Operations Research Center at MIT, and he works on JUMP, which is, I would say, one of Julia's most successful projects in the ecosystem to date. And so what JUMP is it's a modeling language for optimization problems. And so what you do is you use this nice JUMP syntax from within Julia to define an optimization problem. And then what JUMP can do is it will perform automatic differentiation on the JUMP syntax to extract gradient and Hessian information that it can then send to basically box up and send to numeric solvers for you. So if you're doing any type of like optimization work, I highly recommend you check out this package. And so the reason I call it out specifically in this talk is because it uses forward diff to compute the gradients of low-dimensional user-defined functions that you can inject into JUMP syntax, which is pretty nice. So and so. A lot of this talk, actually, I don't know if any of you watched the JuliaCon talks on YouTube, but a lot of this talk I gave at JuliaCon this year. But since then, I've been working on reverse mode AD, actually with the guy that made this this package that Simon called out last talk, Vin Diesel, Fast and Furious, whatever it is that it does. So we're working on reverse mode AD. And I want to brag about it, but I kind of feel like maybe I need to talk about what reverse mode is before I do so. So this is my first time trying to explain reverse mode to an audience, and I will say that I did not understand reverse mode until I like implemented it myself. So I don't know how well this explanation will go over. But so what I've decided to do is really trivially simple case. You wouldn't even use reverse mode for this case. In reality, but it might be a good place to start. So we just have a scalar function of two variables, right? And we want to take the gradient. That's our goal. But we don't know what the function is. And so we've decided we're going to use reverse mode to do it. So what is the process here? So basically, we're going to say A and B are our buddies, and they're going to tell us what happens to them as they trace through the function. And so the way you implement this is via operator overloading, and then you tell you say for your scalar type, you say every time something happens to you, record the thing that happened to you to some tape, so like a vector of instructions or something like this. We're not going to go into the weeds of the implementation, but that's conceptually what's happening. So as we pass in a and b to our function, maybe the first thing that happens is that sine gets called on a, and so it records it, and we're going to store some temporaries here for usage later. And then maybe cosine happens on b, and it records it, so we know that happened. And then we see that the results there got multiplied. Okay, so maybe that's when the function terminates, and so now we know what the function is. Great. We haven't actually taken any derivatives yet, but we're getting there. So now that we know what the function is, we know what the output is, we can essentially say that our partial derivative is a partial derivative with respect to this output, and we know what the form of this output is. So in reverse mode, so in forward mode, we seeded the inputs, and then the derivative information propagated forward. In reverse mode, we seed the output and then propagate the derivative information backwards. It's still an application of the chain rule, just in a different order. So essentially, here we say, okay, we have our we can take the derivative with respect to this guy, right? So we do so, and then we start at that node, and then we push it back up to a higher node, the previous node. And since we know the chain rule will apply here, as I've written it out, we know we can just multiply what we have in the final node here with the derivative that we can take at this current node. And so we do so. So it was just a simple substitution. And then we do the same thing going back up again. Okay, and so now we have essentially these partial derivatives. And so we got that one too. So I think the one thing maybe this example doesn't motivate very well is that this is not symbolic differentiation. I mean, it looks like it is the way I explained it because I kind of mixed code and math. But in reality, what we're propagating backwards is not expressions. We're only propagating values because we happen to know at each step how to take derivatives via operator overloading or what have you.
In this example, don't you actually have to take the derivative of x1 with respect to b as well, even though it doesn't depend on b? The code would really know that.
It doesn't have to. I mean, the algorithm's agnostic, and it will take the derivative with respect to something if it needs to. Like that will come out of the trace information in the forward pass, and then when you go backwards, it all just kind of works because the ordering is preserved. So I hope that answers your question. So maybe that's good. I don't know. Maybe that check mark's a little enthusiastic. So the package has a nice nice name, reverse diff prototype. It's not great to type at the REFL, but the name will change eventually. So it's reverse mode AD written in native Julia for native Julia. The forward pass, as I said before, the way it records that program trace of the forward pass is via operator overloading, and just tell the SCADA type anytime something happens to you, just write it to some external tape that I can then access at the end of the function call. And then the backwards pass is actually essentially an interpreter written in Julia for this tape of instructions that can go forward and backwards through the tape. And so it's an interpreter written in Julia, essentially, which is actually not that complicated when all you're doing is just like going through and multiplying things. So the nodes, so the data structure I use for storing this tape, these nodes can cache an arbitrary amount of storage in the forward pass that then can be used in the backwards pass. So the idea is if I'm doing something like what I was doing before with like sine and cosine, I actually know that I'm going to be using those intermediary derivatives later in the backwards pass. So I might as well calculate, like, so sine, I know that I'm going to be using cosine later at that node. Cosine, I know that I'm going to be using negative sine later at that node. So I can calculate those in the forward pass and then apply them in the backwards pass, which makes the backwards pass non-allocating. Now, why is that important? We have some people working with our group who are trying to get Julia code to natively, transparently compile to the GPU, and their early work is pretty successful. It's not there yet, but it's definitely getting there. And once it is ready for release, the goal is going to be to have these the backwards pass execute on the GPU And so being non-allocating is a very important part of executing things on the GPU. So it supports multivariate optimizations. So I just showed you guys an example of a scalar function taking a derivative, and it recorded just a couple of operations. It's kind of trivial. You would really want to use this method, though, for really high dimensional problems, in which case your tape that you're recording these nodes to is going to be quite long, and that's actually a huge bottleneck for reverse mode. It uses a linear amount of storage in the number of instructions in your original function, which can be quite large compared to the actual code. If you write something like a for loop, you can really compactly express a for loop that has millions of iterations. But if I'm using my tracing method, I don't necessarily know that that's what you've done, and I only pick up the operations that happen to the scalars. And so maybe you write some for loop that takes you this long to write, and then it generates an amount of it generates a tape that crashes your computer because it just takes too much memory to store all those nodes. So there's ways to avoid this, which is to essentially take all these matrix functions that people use normally and calculate their derivatives, and then specifically overload those operations to record kind of what we refer to as fat nodes. So you take these nodes, and instead of recording each individual operation that might happen inside of a matrix multiply, you just take the whole matrix multiply, store it as one node, and then overload the derivative definition for matrix multiply. And so what's cool about this is I would say a fairly common technique, but what's cool about this in Julia is that our optimizations work over generic array types. So you could, for example, use any kind of array that you happen to define, or maybe one that's in base, and it will automatically actually fall back to our optimized methods, which in a lot of cases you can't do that. So this opens up the door for stack allocated arrays and sparse arrays and special structured arrays like banded matrices and all this stuff. So we can optimize in all these cases, and eventually I hope to do so. There are user annotations for enabling optimizations. You can essentially say, hey, this part of the code you can execute totally in forward mode. So you can say, I know that this sub-expression happens to be a scalar sub-expression that you can avoid writing a bunch of nodes for, and you can just write one node for it by calculating the derivatives in the forward pass. And so there are annotations for doing these kinds of tricky things, which are going to probably require a bit of documentation. But and then there's also this thing called constant node elision. So basically, if in this, so you can think of this tape as a tree for some functions and maybe a graph for other functions, and it will, and so there will oftentimes be nodes that pop up in the graph that don't actually lead back to your input. And so these things are worthless for taking the gradient. These are essentially constants. And so we can get rid of those by doing some fancy operator overloading in Julia. And so the performance here is a sight better than forward diff and autograd. And our overhead is fairly low. I will say this is including a full forwards pass and a full reverse pass. In the future, we'll actually be able to do one forwards pass and then save that tape and then just update it back and forth. And I expect that I can basically half the time here and maybe even half that overhead. So maybe it'll be around 5x or so of your original function call. So there's some I don't know how am I doing on time? What time?
Probably another couple of minutes.
Sounds good. So there are some limitations to native AD in Julia. And they're fairly easy to remember. So I can't inject any dual numbers or any fancy scalar types into code that's not Julia code. So if you're doing something like using LPACK directly or calling out to a C library, I can't differentiate it, unfortunately. You can overload derivatives pretty easily for yourself if you would like to, in order to be able to have this work for yourself, if you happen to know the derivatives. But your function must also accept a generic enough input, as long as you are using the real number interface in Julia and not doing anything extremely hard-coded, like converting everything specifically to float for whatever reason, then then it should work. And your function should be type stable. I mean, it doesn't have to be type stable to work, but if it's not type stable, then your code's going to be slow, and that's not good. I mean, that's not what we use Julia for. And so type stability is essentially this notion that the output type can be inferred directly from the input type. So I really want to talk about this, but I don't think I'm going to have time to explain it. Basically, the gist of the story is there's a really subtle bug in a lot of AD implementations called perturbation confusion, where these epsilon components get injected into scopes where they're not supposed to be, and then they interact erroneously and will give you the wrong answer. So the way to avoid this, in simple terms, is you can do differentiation of closures, and you can do differentiation, nested differentiation, but be very careful if you try to mix the two, because you might end up injecting a perturbation from the outer scope into an inner scope, and it will give you the wrong answer silently, which is pretty scary. So we're trying to figure out different ways to solve this now. If you were interested in figuring out what this actually looks like, which is what is described here, you can talk to me afterwards. So in the future, Julia's stack allocated fixed size vectors, there's a lot of different implementations of these right now. But in the future, I think there's going to be something like this in base Julia rather than something external libraries are going to implement, and then we all share the implementation. When that happens, I believe it's probably going to be highly amenable to SIMD vectorization, if any of you know what that is. And so once that happens, it's going to be a huge win for us, because so much of our time is spent just like doing raw scalar multiplies on these fixed size vectors. And so having processor level parallelization for those operations should be quite a big win. So this future work is basically getting that to work. Perturbation confusion, we'd like to fix it. We're trying to find a way to fix it without doing any runtime checks, but also without killing the compiler, because the compiler already works pretty hard to figure out how to optimize this code as it is. So we'd like better parallel support. This is both in terms of having the differentiation be parallelizable and the actually differentiating parallel code. So right now, forward diff actually utilizes, well, it can utilize, if you turn on this experimental flag, essentially, Julia's multi-threading capability, which is not so mature yet, but is eventually, by the time we reach 1.0, it should be ready for prime time. Probably going to document and release reverse diff prototype rather soon as a reverse diff instead of reverse diff prototype, since it will not be a prototype anymore. And so if you care to use this package, be on the lookout for that. And it's going to be really important further down the line to implement this compilation and reuse process of the tape that I was talking about earlier, where you don't have to do a huge forward pass every time to trace the program information just to recalculate gradients of different inputs. So once you trace it one time for data independent functions, they're called, then you don't have to trace it again and again and again, because you know what the program looks like, and so you can reuse that tape. So we still need to implement that. And then GPU support ties basically directly into that. Once we can reuse subgraphs and compile them, then we can basically make it work on the GPU. So if you care about these links, you can probably find them on GitHub under my username under the for diff presentation repository. And there's just links to some of the packages that I talked about. And I'd like to thank everybody in my group, as well as Stephen Johnson, who has generously shared some of his funding with me to keep me funded while I work on this stuff. Miles Lubin and John Pearson are my collaborators for forward diff and reverse diff prototype. And there's lots of contributors to forward diff that I couldn't fit on this slide, but they're all great and make the package way better. And I'd like to also thank you guys for organizing this workshop. It's pretty nice. Yeah, that's it.
I think we should have time for one or two quick questions.
So, if you go back 2 slides, your list of future work.
Yep.
So this question might relate to some math compilation reuse. Would it not be possible to get the same information you get out of doing a forward pass by just looking at the syntax tree, abstract syntax tree of the compiler function?
So Yes, so that is called a source-to-source implementation of reverse mode AD, and there's already a package that does this, but as far as I know, it doesn't handle loops very well, and it doesn't handle ifs very well. So the problem there is if you want to do that, you basically need to write your own compiler for the language you're working with. And someday, like, we might intersperse a source-to-source transformation step inside of this step, which is definitely more easy to apply and much more applicable, I would say. But we've also, compared to the source-to-source transformation, our performance so far has been about the same, really, for a lot of functions, especially for like larger functions. The other really important part of source-to-source transformation is instead of writing out this tape and then doing an interpretation step, you essentially generate code that has a huge amount of temporary variables. And so if you pass that off to the Julia compiler and it tries to do some JIT compilation passes on that, it takes a really long time to compile, like oftentimes longer than it would take just to run the code. So in those cases, it doesn't really make sense to do a source-to-source and compile anyway. But
how easy would it be to extend mathematical differentiation to things like static arrays?
It should work out. It should work out because the yeah, I mean, I can explain to you specifically why, but the idea should be, I'm working on trying to unify an interface for differentiation in Julia at some point, and then allow packages to share testing and benchmark suites. And so what I intend for that interface to support is immutable array-like things, not just abstract arrays, which is what we currently kind of focus on supporting, is mutable abstract arrays. But yeah, I mean that definitely would be a key thing to support for forward mode specifically, where you're already going to be doing like low-dimensional gradients, which are bread and butter for forward mode. So.
Automatically could reduce your chunk sizes. You can keep chunk sizes, but do more dimensions at once.
Yeah. Yeah. So.
Well, thank you. Let's thank our speaker again.
Thanks.